Everybody. So this morning will be chaired by Advenit. Advenit is from ISA, and of course you know Advenit, Makaya, and the session is construction and manufacturing. As with the last couple of days, it'll be about 10 minutes of a talk and then a very activated couple of minutes of Q&A. And I know that over the last 2 days, you've been just truly superb at being actively asking questions, which is really wonderful. Kind questions, of course, just probing questions, but on the nice side. So with that, I hand over to Advenit, but I do encourage anybody coming in to sit centrally and as close as possible to the stage, because it's just really lovely for the speakers to have an audience. Thank you. Advenit.
Thank you very much, Lisa. Thank you for coming to the most interesting session of the conference, but a bit biased. But I think we have a very good lineup, which shows the progress we are making in the maturity of the manufacturing technologies and also the breadth of the materials we can cover. So hopefully we get a sample of that this morning. And our first speaker is Timon Schild from Esric, who will tell us a bit about metal extracted from regolith. Timon.
Hello, good morning everyone. Thanks for making it that early in the morning. So I'm Timon Schild. I'm a PhD candidate here in Luxembourg at Esric, and I'm going to talk a bit about our work on the FFC molten salt electrolysis process, and specifically on the metal production aspect of this process. So for a bit of context, some of you may be familiar with this. This is a diagram of the FFC process, which is used to turn, or to extract rather, oxygen from lunar regolith, or in our case, lunar regolith simulant. And as a byproduct, you also get all the metals that were present in your feedstock collected at the cathode. What our project is looking at is taking those metallic byproducts and turning them into a feedstock that we could use for additive manufacturing. So in this talk, I'm going to talk about, first of all, the characteristics of this product, the investigations we did to look into the melting behavior of those for the casting and forming of those alloys, and finally a little sneak peek into some early results on laser interaction. So to begin with, I'm going to do a very quick summary of my presentation from last year, which was all about the characterization of those materials. So what we did, we ran the FFC process at a lab scale on LHS1, regolith simulant. And when you do this, so you electrolyze it in calcium chloride, in our case for 24 hours, and you end up with this kind of material. So metallic powder or granulate that looks very heterogeneous as it is, and even more so if you take it under the microscope. So here you can see the abundance of all the different metallic phases that you have in there, all mixed together. I'm not going to go too much into details about that. We have a publication that came out earlier this year. I obviously invite you to have a look at it, and afterwards I'm happy to discuss some parts of that. The only thing I'm going to tell is the average bulk composition we observed in this material is, as you expect, most of the metals you put in come out. So you get mostly aluminum, silicon, calcium, and iron, as well as some contaminants from the process. So now I'm going to talk about what we've been doing during this current year. So we have been looking at the thermal post-processing of this material and how we can turn it into an ingot or a billet that can be used for manufacturing. So the first thing we did is we took metals, off-the-shelf metal granulates, and mixed them in the proportions that we observed in our product. So a mixture of aluminum, silicon, calcium, and iron, and applied different temperatures to it. And we observed that slightly above 1000 degrees C, when we heat it under inert atmosphere, we were able to produce this nicely molten ingot. Here you have a cross-section of it as well. And when we look at it under SEM, we see isotropic distribution of metallic phases, no real phase, no clear, let's say, vertical phase separation, and you also see complete consolidation. So it forms a nice melt pool and consolidates to a solid ingot. This is nice. This is kind of what we were looking for to get from our products out of the FFC process, but when you apply similar post-processing to actual products coming out of the FFC process, things get a bit more complicated. Here, just for the composition, again, not many changes. We get out what we put in, so we don't have many losses. We do have a slight decrease in calcium, but that's also within the measurement margins. So as I said, if we apply this to actual products that come out of the FFC process, here we took some reduced LHS1 and also applied different temperature profiles, but there we observed that even if you go all the way up to 1,415 degrees C, which is kind of the limit of our instrument, we do get consolidation, but what we can see is that we get more of a semi-molten, sintered ingot rather than nicely consolidated billet. This is what it looks under SEM. A few interesting features we can see there. First of all, we can see it's still quite porous, although it has partially molten in some places. And we can also see a vertical segregation. So we see a separate phase collecting at the bottom of the crucible there. Compositionally, so again on the left you have the starting composition that we measured in the material. A few interesting things in the bulk material in the red region, we see a significant decrease in calcium, which on one hand is explained by the pooling of a very calcium-rich phase at the bottom, but we also expect at the temperatures that I'm discussing here, we also expect some significant evaporation of the calcium. I'm not going to discuss the lower temperatures that we tried, but in a nutshell, it's the lower you go in temperature, the less and less it is consolidated. So to summarize this part of the work, on the left we have the results with a kind of idealized mixture of aluminium, silicon, calcium, and iron, and on the right what we actually observed with reduced LHS1. We can see on one side we get, as expected, a nice melting and ingot formation, slightly above 1,000 degrees C, whereas with actual products from the FFC process, the consolidation happens, but not fully, and we don't have a nice melt pool formation, even as high as 1,400 degrees. We also observe a phase separation that we do not expect from the idealized mixture, where the phase distribution is isotropic. So to conclude on that part of the talk, we expect that we have some elements in presence in the reduced regolith that prevent regolith simulant, that prevent the melting. Our main suspects, let's say, are the residual oxygen content. We still have over 1% oxygen in there, so 1 to 4 weight %. It could also be surface reoxidation during the post-processing, as well as the presence of different contaminants. I'm thinking stainless steel components from the reactor. So still some investigation to do there, but we still continued pushing forward in parallel, and we started looking at the end application, the additive manufacturing. So here I'm going to talk a bit about Metal 3D, which is additive manufacturing system built by Airbus Defence and Space, and that is currently on the ISS and 3D printing metallic parts on the ISS. And the way this process works, it's a wire laser-based process. So you have a substrate in the flight model. It's a stainless steel substrate on which you impinge a laser beam that forms a melt pool, and then you feed some wire in the flight model, stainless steel wire into it to form the parts that you can see here on the left. So we have been using the engineering model or a prototype of the same system, and we applied it to our idealized aluminum, silicon, calcium, iron mixtures. So we replaced the substrate by an ingot of our mixture, and we replaced the wire by an aluminum silicon wire, a commercial 12% silicon aluminum alloy. And so here I'm going to show kind of the very early results from that. And I have a video about the deposition, what this deposition process looks like. So here we can see we're forming a melt pool and then slowly feeding the wire in it, and here it's just a first layer. The main thing to observe here is we get a very nice melting of the substrate and a kind of very nice weld bead in a way deposited on it. If we look at the kind of samples we obtained, again, that's kind of the first sample we got. So obviously there's room for improvement. So on the left side of the sample, you can see single beads deposited. And then on the right-hand side, we tried stacking 2 layers on top of it. If we look at the section of this under SEM, that's what it looks like. And we can see 3 distinct regions. On the bottom, you have the substrate, which is very similar to the ingot I showed earlier. And then the interesting part is the first layer is very well mixed between the aluminum alloy and the substrate with very good adherence and kind of mixing of the material. And when you look at the second layer, we can actually see that the metal wire we're depositing adheres less well to itself than it adheres to the substrate. So that's quite an interesting result for us, showing that the material does have potential for additive manufacturing. So the 2 conclusions I'm taking from this work, first of all, the melting behavior of the metals that come directly out of the FFC process is not trivial and still needs some work. Our suspects, as I said, are residual oxygen content or contaminants from the process. But if we can solve this step, the metal ingots we are expecting to get at the end of this work actually should be quite suited to the wire laser-based additive manufacturing process, especially we get a very nice melting behavior. I'm going to leave with that. Thank you very much for your attention, and I'm happy to take some questions.
Thank you very much, Timon. Exciting presentation. Just to remind everybody, so far no one has manufactured something with reduced regolith metallic alloy, so the challenge is still open. Questions from the audience? We have one in the front from Aaron, and then one from Miranda.
So I'm Aaron Shamatsi, and my question is, did you have a chance or did you attempt to do the melting of the product in argon atmosphere, for example, in an argon glow box, where you can control the atmosphere to avoid potentially the surface reoxidation?
So the melting process I've been showing, we did it actually in helium. Helium 6.0, so actually a lot of our work was making sure that the oxidation is not actually coming from the outside and not related to our setup, but that it is actually a behavior of the material itself.
Mm-hmm. Yeah. Okay, thanks.
Thank you, Aaron. Miranda, just behind you.
Congratulations on the very interesting work. I was wondering what's the size of the wire, the diameter, and how did you produce the wire itself?
So what I've been showing with the wire, so the wire is a commercial wire. So we did not yet produce the wire from our actual material, but that's actually one of our next steps, trying to crack this nut, let's say. And the diameter of the wire, that's process information on the Airbus side, so I don't think I can tell anything on that.
Thank you.
Thank you very much. For the sake of time, we move on. Timon is available for further questions. Thank you, Timon.
Thanks.
And our next speaker is Juan Carlos Arañó Romero from the German Aerospace Center, who will tell us about composites.
Thank you very much for the kind introduction. So my name is Juan Carlos. I'm a PhD candidate at the newly formed Institute of Frontier Materials in Space, on Earth and in Space. It's a merge of the old Institute of Material Physics in Space and the Institute of Material Research from the German Aerospace Center. And my PhD director is Professor Mathieu, and my supervisor is Alexander Niecke, who will be presenting afterwards. So I will be discussed today about the production and characterization that we have performed of fiber-reinforced ceramic matrix composites made from lunar regolith simulant EAC1A. So on a paper published on 2022 by the great Israeli researcher from Florida Space Institute, Philip Metzger, he discussed the theoretical lunar landing pad for the lunar surface with a 50 tons lander. In this paper, he discussed the requirements for this surface that should be at least high temperature resistance, temperature shock resistance, as well as pressure shock resistance to withstand the heavy weight of the lunar lander. And he also mentions estimation of a radius of 27 meters for the surface that will be translated into 170 square meters. So from this example, what I'm trying to explain that for future lunar missions, we will need materials that will be strong, thermally stable, and if possible, locally sourced due to the huge quantity of material we'll require. And the promising option that I will discuss here is the use of ceramic matrix composites, shortly mentioned as CMC, that are made from lunar regolith. So these talks cover 5 key points, which is why lunar regolith is relevant, what are CMCs, how we produce them, what we found, and then what this means for space exploration. So let's start with why lunar regolith could be such a promising material. So lunar regolith is rich in useful oxides, and they're readily available. So it's perfect for in situ resource utilization. And this table here compares the oxide composition of actual lunar samples with our raw material used during these experiments, the EAC1A. As you can see, it contains silicium oxide, aluminum oxide, and iron oxides in a comparable range, specifically closer to Maëlle regolith. And now we can see that typical silicate ceramics are also in a comparable range. The typical oxide composition, as well as the typical chemical composition for basalt used on the continuous filament production here on Earth. So this makes lunar regolith suitable for producing the materials that we require for the CMC's production, as well as the readily availability. So let's talk about what CMCs are and why they matter. So CMCs are an advanced material designed to overcome the natural brittleness of the ceramics. So it's a combination of a ceramic matrix with a reinforcement phase. In the case of this study, I will talk of short fibers. So by adding fibers, we are using the reinforcement strategy of improving the crack resistance on the ceramic. And these strategies are, for example, bridging cracks, as you can see in the diagram, which prevent the spreading of the crack, as well as deflecting the crack propagation, in which the fiber absorbs the energy of the crack by spreading this energy over the interface between the fiber and the ceramic. So thus, we can improve the toughness as well as the strength and the thermal stability of the material, of the ceramic. And then this means that the material will be more efficient because we can produce components that require less mass, but also having a comparable toughness and same performance as another component with higher mass. So because of these properties, CMCs are usually used on Earth in demanding environments, especially for thermal protections. structural panels, and components that are facing usually temperature, extreme temperature and loads. So in our case, we wanted to make such composites. So let's take a look at our methods and materials. Okay. So as we already explained, our material is made of lunar regolith simulant, EAC, as well as short fibers that have been, short basaltic glass fibers that have been made from the same material. And in this picture, you can see in an illustrative way the material that we use. I mean, the samples were not exactly prepared like that, but this picture was especially nice because you can see both components. And these fibers were uncoated and have been randomly spread over the layer of lunar regolith. So the diagram summarized basically the process, which was we layer the powder, which was previously dried. Then we spread, as I mentioned, randomly over the layer powder layer, as well as we compact each of the layers. Then we sinter the whole structure under different conditions, and with this setup, we produce multiple samples. So let's take a look at how they perform. So the mechanical resource of our sinter samples will be described, and how the fiber reinforcements improve them. So first, the fibers, with fibers, we saw improved performance. So the samples that tolerated more strain and reach a higher strength in comparison with the samples that were not without fiber reinforcement. Interestingly, there was the holding time during the sintering, the thermal treatment, didn't have much effect on the performance across different particle sizes. But higher sintering temperature actually clearly led to an improvement of the compressive strength, which could be due to the higher liquid phase. And there was also a significant strength gap depending on the particle size. Logically, as could be expected, finer particles gave better results because there was a higher surface area, and then the particles could bond better. And then we also researched under the microscope the raw material, and we saw that it actually has a smoother surface than real regolith, and that actually helps on the densification of the sample during sintering. So in the top picture, you can actually see a sample, one of the tiles that we produced with a homogeneous surface and quite flat. And then in the bottom, one of the pictures that we used during the microscopy analysis. So these results make us look more closely on what happened to the material during the sintering, and which lead us to the thermal behavior. So to understand the sintering behavior, we ran a differential scanning calorimetry up to 1,500 degrees Celsius, and this curve shows a complex thermal response. And this is due to the EAC1A being a mixture of many minerals. So you can see also a wide sintering window, meaning there is flexibility in processing temperature. And through TGA, through thermogravimetric analysis, we also saw that most of the outgassing happened up to 650 degrees Celsius. So this is good, especially under vacuum, because then the material could be pre-treated in order to help on a better densification when sintering under vacuum. Also, we ran some XRD, X-ray diffraction, in order to see like the mineral phases in different particles fractions, and we saw that the bulk material have 5 dominant phases, but the finer fractions, they have mostly pyroxene and plagioclase. So this thermal result supports our mechanical findings, and we can show the potential for processing this material under space conditions. So I don't have much time, so I'm just going to go really fast on the implications for the lunar missions. So basically, we are able to produce structural panels, as I discussed, thermal shields, as well as equipment housings for future lunar settlements. And the benefits are quite clear, that we can use the local material use, we can reduce the transport costs, which will make it more viable, economically viable, and it has capability with additive manufacturing, which is a project that we are currently working, which is quite exciting, but we're not going to discuss today about it. But you can ask me afterwards, of course. And the final takeaways, the lunar regolith base CMCs are working, like fiber reinforcement actually works. So it improves the mechanical strength and the strain tolerance, and thermal analysis confirms some of the behavior of the material and a better understanding under vacuum. And yeah, these results support that we should further develop these technologies for future applications in space and on the moon. So thank you very much. I hope that we just wanted to say that we actually can build where we land, and moon dust is actually one of the material to use. So thank you very much.
Thank you very much, Juan Carlos. I'm glad that you're talking about landing pads. I think Jerry's presentation showed that it was somewhat down on the list, but at least to me, that's an important aspect. So Jerry, first question.
There we go. I may have missed it, but it appeared that you had a box filled with regolith and you put basaltic fibers on top of that. Did you bake that in an oven? How did you do the sintering? And if you are making tiles, why didn't you actually spend a little bit more time kind of putting a layer of regolith, basaltic fibers, a layer of regolith, basaltic fibers kind of thing to get a true matrix versus just spreading it on the surface?
Okay, thank you for your question. So the picture that I showed, it was illustrative. It was not actually how I did my experiments. It's just like, it was the nicest picture where you could see both materials before sintering. Yes, but no, the samples for these experiments were used under, the thermal treatment for these experiments were done in an electrically heated furnace. And it was made in a layer-wise approach because it's also related with one of the of a project that we're performing, which is on 3D printing, but as well because it's quite important on a fiber-reinforced composite that the fibers are spread homogeneously, and this was the best approach that I found, like where I could assure that the fibers were actually homogeneously spread.
One more question from Clive.
Yeah, very interesting talk. I have a couple of questions, but we'll be quick to answer. If we go to the South Pole, there's no basalt there. So have you looked at using fibers made out of the material itself? And the other thing that struck me as you were going through this, and actually in the previous presentation, the capability to do 3D imaging of the entire thing through X-ray computed tomography is something that would be really interesting to see the distribution of the fibers after you've done the sintering. And I don't know whether you've considered that or if that is a possibility, but to get that 3D imaging of what you're actually producing to show the consistency, and then you can interpret your strength, because launch and landing pads are probably the most critical initial infrastructure that's going to be needed if we keep going back to the same place.
Yes, so if I understood correctly, the Shackleton crater, it's one of the most promising, or especially the rims, it's one of the most promising landing areas, and it's because of having sunlight 24/7 and also some shadow areas. So yes, I think that that's a good approach.
I think the question was, do you find the basalt to make your fibers there?
If so, I don't know about a specific chemical. right.
So that's why you make the fibers out of your material, either high grading that material to make your fibers distinct. That may be a way to use local materials completely rather than having to bring it with you. But that's, as I say, that's something to consider.
Yes, okay. But yes, we are also going to consider using computer tomography and NanoTAM CT to analyze the position of the fibers.
Thank you very much for the question. Thank you very much, Juan Carlos.
Thank you. Sorry.
And we move to the next talk by Marvin Raupert from Leibniz University, Hannover, who will tell us about laser powder direct energy deposition.
Okay, thank you, Advenit, and good morning to all of you. So in the next 10 minutes, I show you our progress in the in-space manufacturing of or by laser powder directed energy deposition. And therefore, I would like to start with the following question. So why is directed energy deposition relevant for the in-space manufacturing? So the simple answer is that we have a lot of opportunities with just one additive manufacturing process, like manufacturing, coating, joining, modifying, functionalizing, and repairing. And for those who are not familiar with this process, so it's a process where free-form nozzle deposits molten material on the desired surface where it then solidifies. And the technique differs in the heat source and the feedstock shape, which could be wire or powder. So why should we use powder instead of wire? So for both shapes, there are several advantages and disadvantages. For example, for the wire-based feedstock shape, there's a higher material utilization. It's easier in handling in reduced gravity or in storaging. And when we're talking about the powder-based shape, then we have a higher material variety, resolution, precision, and it's more well suited in for functional graded materials and for in-space manufacturing utilizing in situ resource utilization. So we're coming to the main question of my talk. Does gravity have an influence on the laser powder directed energy deposition? For example, microgravity on space stations or lunar and Martian gravity. And that's the aim of our research project. So determining the influence of gravity on the LPDD process and the materials used, especially the melt pool dynamics and powder flow dynamics. And this project is a cooperation between the Leibniz University of Hannover, where I'm coming from, and the Otto von Guericke University of Magdeburg, and is funded by the DFG. So how is microgravity simulated? That's important because we want to get to know the influence of gravity, so that we're doing at our drop tower facility located in Hannover, which is also part of the research infrastructure of the university. And that's an active drop tower facility with a height of 40 meters, with a drive system over the whole length. And there we have the opportunity to do everything between microgravity and up to 5G. And for microgravity flights, then we have a maximum of 4 seconds of microgravity with a residual acceleration of 10 to the power of -6 G. And with the help of the drive system, we are able to do up to 300 flights in 24 hours. And we have a huge payload capacity with a carrier dimension of up to 1.7 meter in diameter and 2 meter in the height and up to 1,000 kilogram. And we do offer third-party use, so if you are interested, feel free to contact us. That's the preparation. So the experimental setup goes on top of our base structure, where several units are in, like the flight computer, heat exchanger systems, battery, and so on. Then we are able to do or to put on a pressure-tight shell for an acoustic decoupling, additional to the mechanical decoupling. Then the whole system goes into the gondola system, which you can see on the third picture, and then we are ready for flight. And that's how it's looking like. So we accelerate the gondola with 5G for half a second, for the first 5 meters. And then the inner part, the experiment is set up, will decouple from the bottom of the gondola, and we are on free flight. 2 seconds to the highest position, then it's falling again 2 seconds, so in sum 4 seconds for microgravity. And that's a small example, a bottle filled with water and a small amount of air. And then in microgravity, the air is forming a perfectly formed sphere. So, in my case, the clicker is not working. Come on. Okay, so how are the specimens manufactured in microgravity? This is a setup you have already seen with several units, like the control system. We have a cooling system for cooling down the laser system, the fiber, the nozzle, and the optics. And then a diode laser with a maximum power of 2000 watt. The diode laser has its own energy storage. We have a manipulator on board to do not open the process chamber and the gondola every time we have manufactured a specimen. Then the process chamber for not contaminating the environment and for having a shielding gas atmosphere, a powder conveyor, and the pneumatic system, which is part of the powder conveyor. The powder handling we had to build completely new because the common systems here on Earth do not function in microgravity. So therefore we have built 2 prototypes. The first one is a spiral scraper, where we have a powder container which could rotate and move up and down. And with the help of the Archimedean geometry, you can see in green on the left lower corner, if we are rotating this geometry, then the powder goes into the center, and then if we are moving it up, then we could catch the particles with the help of the argon volume stream. And the second prototype is a rotating disc, where we are having up to 4 powder containers. And then we are rotating the disc. The particles are going to the outer part. We have again some argon tubes catching the powder. The mixture is going back into the center and to the outlet. And that's how it's looking like if we are rotating this. We are using the spiral scraper for our first flight campaign. And that's how it's looking like. So this is a worldwide first application of the laser powder directed energy deposition in microgravity. In this case with titanium 6-4. And you can see that we are only able to print a small section with the small height of the specimen, but we can do several flights to increase our height of the specimen. So the question is, can laser powder directed energy deposition be used in the in-space manufacturing? And the answer is, like you have seen, yes, we can. Here again on the left side, you can see the manufacturing duration. So we only printed for the first section 1.5 seconds to have enough time for cooling down our melt pool. This is the temperature is in the blue curve, and the induced acceleration is in the red curve. And there you can see that the temperature drops to the amount that the 5G deacceleration of the drop tower facility has no influence anymore. Then on the right side, you can see the specimens. We manufactured specimens under microgravity and under 1G with the identical parameter settings, and after it we compare the specimens with each other. So in the microstructure we have seen no substantial differences. Also, we have done some density analysis via CT scans, and there, again, with no substantial differences. We have done some vigorous hardness tests, and there we have seen a higher hardness value in all the 7 measuring positions. Therefore, we have 2 reasons. First one is that the powder flow mass increases due to the powder feeder working in free fall. So there we have a little bit, the volume of the specimen is a little bit higher. We're working on that, but it could be, reason 2, that there are different melt pool dynamics, because in microgravity there's only the Marangoni flow and no buoyancy flow. So what are the next steps? Currently we're working on our experimental setup to optimize it, to have a deeper understanding of the gravity influence, especially the melt pool dynamics and powder flow dynamics. And we also want to print with lunar regulus, Martian regulus, and shape memory alloys like nitinol. And with that, thank you for your attention.
Thank you very much, Marvin, and thanks for keeping the time. Do we have any questions from the room? Yes. Timon.
Yes, Timon, Schild, Esrik. Thank you very much. A very interesting presentation. I was wondering, during the powder deposition, do you have any loss? So how much of the powder actually ends up in your part, and do you have some that ends up in your building chamber? And if so, do you already have an idea on how you would recollect that in reduced gravity?
Yeah, so therefore we have the pneumatic system. So we collect the powder before we manufacturing, and just a few seconds before we activate the laser, the powder then goes to the melt pool. We are working on an analysis where we want to find the efficient comparing microgravity and 1G of the powder, if there is an influence of the microgravity. But yeah, we haven't done this so far. What was the other question?
The other question was, if you do have some loss, how are you planning to recirculate it back, or what you're planning to do with material that doesn't end up in your in the deposition?
Oh, there's a cyclone system, okay. And then we collect it and we could use it again. Yeah.
Yeah, but I guess the overlying question is, if you do it in an actual orbital manufacturing setup, the powder handling becomes very challenging for the lost powder, which will essentially float in the air. So how do you plan to address that?
Yeah, that's a good question. So I guess when we are on the moon or on the Mars, there we have not a big problem because there's a lot of regulus. But in space stations, yeah, you have to print in a process chamber, and you have to put all the particles in the recycling system in a cyclone, and just 1 second before you print, you could put the way or open the way to the melt pool. I think that's the efficient there is not that high in comparison to wire, but there you have no other choice. Yeah.
Thank you very much, Marvin. Thanks again. And we move on to the next speaker. So a round of applause for Marvin. Our next speaker is from the University of Tokyo, Lucas Brian Christen, and we saw with the first presentation that the reduced regolith is a very complex alloy. And Lucas will tell us a little bit on selective metal extraction.
Thank you for the introduction, and thank you for having me here. I'm very happy to share our research on metal oxide extraction from regolith using laser from the University of Tokyo. And so, yeah, this topic deals with a process to refine regolith on an elemental level to feed it to subsequent processes. One of them, for example, being molten salt electrolysis. We just previously had the talk, so it's very nice. So the current approach is that we take the raw regolith feedstock and we feed it to the electrolysis reactor to produce our metal alloys and oxygen. However, the alloys that we produce have a very complex composition and very hard to deal with. And in order to kind of prevent that or to create better, higher purity metal alloys, we propose to put a pre-stage in front of various methods, such as electrolysis, to refine the regolith. And so the idea is to put the raw regolith through this refinement process, really extract some materials on the elemental level, so alter the chemical composition, and then end up with, for example, 2 separate feedstocks that we can individually feed into an electrolysis reactor to produce higher purity metal alloys. And the approach that we take is rather unconventional. We propose the use of continuous wave laser ablation at atmospheric pressure. And the idea is to simply irradiate, it's pretty straightforward, simply irradiate a laser continuously onto the regolith. And what happens is that we deposit lots of energy inside the regolith, and it ejects a sort of ablation plume that consists not only of vapor, but also of reduced species, because CW laser ablation covers the boiling area, but just as well goes into pyrolysis, so into decomposition and reduction. And so the advantage of this method would be that we require no consumables, basically, because we only rely on thermal energy. We are scalable through only the laser power, for future scalability. And we can also operate continuous wave lasers solar pumped. So through the use of solar light, we can excite the optical medium of the laser. So we do not rely solely on electricity. And what we can do with this process would be to extract oxides that we have present in the regolith, as we can see here on the table, selectively through boiling. So simply by raising the temperature of the regolith, it's a very simplified approach, we extract the oxide through boiling. And if we simplify this now, taking a look at only anorthosite, so this is the table. We see the boiling points according to the oxides that are present in the regolith on atmospheric pressure. And if we simplify this now using only anorthosite, which has silicon dioxide, calcium oxide, and alumina, or anorthite. And so in this sense, we would take a first stage to boil out, sort of say, the first oxide according to this table, silicon dioxide, and which leaves us with a residue containing only of aluminum, calcium, and oxygen, and perform a second stage to boil out the next oxide according to this table, leaving us with 3 refined materials, ideally. So this is the idea, and we tried this doing some experiments, not on anorthite or anorthosite, but on Mars-type simulants for now, being EAC1A, FJS1, and JSC2A, and we took the powder and sintered them into solid pellets, mainly for the convenience of the experiments, and placed these into a 20-liter cylindrical vacuum chamber. You can see a rather close-up of that in here in the picture. So these were simply placed in the chamber. We mounted a collection plate on the top to adhere the species that we extract through this method, and irradiate the laser onto the sample. The laser is a 1.5 kilowatt fiber laser with a wavelength of 1080 nanometer, and at a spot size of 5 millimeter diameter, we can create an intensity of 8 kilowatt per square centimeter. And then we measured the temperature using a pyrometer of the surface and a spectrometer to see what kind of species we produce. So the analytical methods would be pyrometry for surface temperature measurement, emission spectrum to see what kind of species do we have, do we even have thermal reduction present, and most importantly, SEM EDX of the collected material to see what do we actually extract at the chosen conditions. And so for now, what we did is sort of a preheating prior to the large intensity radiation at 10% of the laser power, to sort of slowly heat the sample and prevent cracking before we utilize the full power. So then eventually switched on the full laser power, and we reached the temperature of 2,800 Kelvin roughly. And some images you can see here during the process at 30 seconds is basically what illustrates this 2,800 Kelvin point. And this exceeds, of course, some of the boiling points of the boiling point table that we saw earlier. So naturally, we would assume that at least these species are somehow present in this plume that we see here in the pictures. And we do see that in the emission spectrum partly that we measured here 10 millimeter above the surface. And so we see mostly sodium and potassium present, strongly radiating in this spectrum, and also lots of smaller peaks that were not all identified, some of which we believe to be iron. But again, most importantly, potassium and sodium we see that matches with the boiling points, and moreover, they are obviously thermally reduced if they were present as an oxide before. And however, what we did not see is silicon. So we saw earlier we exceeded the boiling point of silicon dioxide. However, silicon was not detected in the spectrum. But still, the question remains, was it extracted or not? So that leads us to the last analytical method of the SEM, EDX, of the collection plate. And so what we adhere to the plate is this white, finely grained powder. So notably white, very different from Mars simulants. And so we did the SEM, which is very homogeneous adhesion at micrometer scale. And the EDX point analysis and mapping shows us that we have a composition as shown here. So actually most of the metallic components is silicon. So this is very interesting because we can obviously extract one of the major components of regolith and really refine regolith into multiple feedstocks. And most importantly here being silicon, and additionally also the alkalines and iron apparently as well, and phosphorus. And so that already concludes my talk. So we were able to extract oxides, of which we believe we did not perform XRD to find out yet. We're on the way. Silicon dioxide, sodium oxide, potassium oxide. And it seems that the boiling points of these oxides align very well with the surface temperature that we got. So we believe that there is, that we can actually refine regolith based on these boiling points of these oxides to a certain extent. And that means that we can refine regolith through laser ablation, that it is feasible, and that is something that we should look further into, and that prospects that we can combine certain methods in order to produce higher purity metal alloys. And one last word about the future work. So this was only a single stage extraction method, but the idea would be to really tackle precisely the temperature and try to find out how to extract these materials, oxides, in multiple stages selectively, to really purify what we get. And that is already my talk, so thank you very much for your attention.
Thank you. Thank you very much, Lucas. Do we have any questions from Lucas in the audience? Yes, Timon.
Hey, thank you very much for your very interesting presentation. I had one question. Did you also characterize what was left over? Kind of the
residue.
solid? Yeah, exactly, and maybe the bulk composition of that to also see what has been depleted on the other side, and also if it matches what you're collecting on your plate.
Yeah, actually, so we did try that. That was one of the analytical methods that we also performed. However, I did not include it here because the result wasn't very promising, let's say. We did find a deficiency of actually silicon, potassium, and sodium. So just as basically the adhesion that we saw. However, the data wasn't very precise. So, and in order to, what we want to do is, in order to really see this deficiency in the residue, is do long-term extraction. And that we haven't really done so far. We're working on it, but it's quite difficult to get it working. Yeah. Thank you.
Do we have any other question from Lucas? Yes, Robert.
Thank you for the talk. One thing which was not really clear to me is because you zap your sample with a laser and essentially you boil off more or less everything. So for me, it wasn't entirely clear how you do the or how you could do maybe in the future the temperature control to have a staged really evaporation of the different phases.
Yeah, thank you for the question. So at the moment, actually, at this laser intensity, we reach a certain level, and doing this continuously, we can extract certain materials. And but actually, what we believe is that once these materials are extracted, that the latent heat of the residue changes, and actually at the same laser power we expect higher temperatures due to less endothermic reactions inside the material and less the change of the latent heat, melting and boiling. And through the change of the material we can and controlling the laser intensity we can really
that's exactly the point. So by tuning the laser intensity, you may be able to control the process better then.
Yes, we're working on a PID-regulated process that measures the temperature using the pyrometer, feeds it back, and controls the laser output to really achieve a constant regular temperature over time.
Yeah.
Right. So yes, that is the idea.
Okay.
Thank you.
Thank you very much, Lucas. For the sake of time, we move to the
Thank you so much.
next speaker. And we had a question earlier about the representativeness of the material used to make the fiber. So I think the next talk will help answer that from Alexander Niecke from the German Aerospace Center.
Thank you very much, Advenit, and for the kind introduction, and also to my colleague Juan Carlos. He already introduced our department at DLR. So my talk today is about the production and mechanical characterization of glass fibers derived from lunar regolith. And I think that the production of fibers, basaltic fibers, is in fact a good example of ISO application, and therefore I'm going to explain in the following slides how to produce and optimize, maybe too, silicate endless fibers in a hot, high temperature process. So we are talking about fibrous materials and their application, and at this point I would also mention that in the talk from Robert Brühl from the Fiber Code company already introduced this topic very detailed, but to summarize what was said, fibrous materials can be used in different and multiple applications for producing geotextiles, for instance. In this context of a lunar habitat, geotextiles could contribute to, for instance, to optimize, to modify the infrastructure around lunar bases, for instance, but fibrous materials made from simulant or real lunar regolith could also use to produce wool for filtration application of gaseous or aqueous media. But after all, it can really be useful for reinforcement application as both states as endless fibers and as short fibers. But it can also be used as hydroponic substrates for plant cultivation. So the technology of producing endless fibers is quite well established on an industrial scale. On the industrial scale, the first step for production is to work on the exploration of raw materials, to mine raw materials that are suitable for this kind of production and for this type of production of endless fibers. Next step is mixing these refined raw materials, which is a quite costly and expensive process. After this, in the next step, all these ingredients are batched and heated up and melted and conveyed to a fiber-forming area on the industrial scale, where fibers are produced in so-called bushings. Bushing is a kind of a box that has a metal plate with many holes, orifices, and the melt is extruded through this bushing, and filaments that are extruded, that are formed in this process, are collected. We have developed on a lab scale a system that, in cooperation with the University of Aachen, RWTH Aachen University, that is capable to spin fibers of basaltic composition. But this process is slightly different, as you can see in the slide, as the industrial process. The design can be seen on this slide, and it consists of a cooling unit, a generator, an oscillator that is transforming the current in a high frequency current that is used in the inductor, the heating system, which is composed of a coil and one crucible, a small bushing, where the melt is extruded and then collected using a winder. And you can see that we produced from basalt, from simulant, our small feedstock, that this material was first vitrified, and in a second step is introduced into this system to extrude the melt and to spin fibers. So the conceptual sketch that you have seen was now realized, and we, as a demonstrator and a lab-scaled furnace, and it consists of a winder again, and the inductor and a housing system around the inductor and the coil. And it can be noticed that the temperature are quite high in this inductor. We can run this system at 1450 degrees C, and you can also see on this slide that the temperature gradient are quite big. This is due to this system. So our next step will be to incorporate these parts of this apparatus into a vacuum box or vacuum chamber in order to reduce the spinning temperatures and optimize the spinning process later on. So how does it work, this spinning process? You can see here on this slide the inductor and the you see the inductor and the crucible, which is a one-hole bushing, and there is a sequence of some images that show how this extrusion works. And first, we have the formation of a droplet at the outlet of the nozzle. In the second step, this droplet is growing, and is growing until it gets a critical mass and folds down in the direction of the winder. At the same time, the glass jet that is coming from the nozzle is elongated, and continuously a small fiber is formed. So this is a situation when this process is well balanced, and as we cannot really see on these slides, on this slide, the formation of the droplet, I added this at the right part of this slide again to see it in more detail, how this first droplet is formed, and in the final stage, in a equilibrated stage, the shape of the cone looks like is very well formed and looks like a perfect cone. To assess if this system is really working, there is a simple formula to calculate the forming gap or the temperature range in which this process might be stable. That means you have to determine the forming temperature based on the viscosity, depending on the chemistry, and the liquidus temperature. And this forming gap should be more or less 50 degrees C. The better, the higher, but 50 degrees C is already a good temperature. So in case that this process is not balanced, that can happen. You see these imperfections in the glass jet that is extruded to the nozzle. These fluctuation of the size of this glass jet can be due to the chemistry, chemical variation, to the chemistry and inconsistent chemistry due to the temperature. So, okay, these glasses, these simulants were prepared. We prepared EAC1, LHS1, LMS1, and TUPS-M from powdery materials. We melted these to form glasses, and we were able to produce fibers from EAC1, but as you can see, small imperfections are visible on this picture on the right side. We produced several grams, but the process, this material has some inconsistencies, so that endless fibers of textile quality were not possible in large quantities. In contrast, we modified the EAC1 composition and were able to produce endless fibers of textile quality with high E modulus and relatively high tensile strengths. The same for the LHS1. For this simulant, much more elevated temperature I needed because the liquidus temperature and the forming temperature are quite close. but nevertheless, we were able, by modifying the setup of our experiment, to produce also in bigger quantities, textile-grade quality, endless fibers. LMS1 was also possible to be produced. You see more in detail these imperfections, and you also see that macroscopically you see imperfections, and also on the microscopic scale using light microscopy detect imperfections and inclusions are visible, and these inclusions are have a detrimental effect on the spinability. TUPS-M is one material that could be fiberized in large quantities, and we were even able to produce simple composite materials and build up some composites for demonstration in a sandwich structure. This is a rough summary of the mechanical properties that we obtained, and LMS1 seems to be to have the best immodulus values, and as reference I added the E-glass standard with 75 gigapascal. So conclusions are that the continuous fibers are indispensable for structural and construction materials. Processing continuous fibers using simulants was possible. All simulants were fiberizable, however thermal parameters are unique for each simulant. More investigations of the glass forming ability are necessary to better understand the spinability and how to optimize the mechanical properties. Current experimental setup will be adapted for spinning in vacuum and therefore lowering the spinning temperatures. Thank you very much.
Thank you very much, Alexander. We have time for a couple of questions. Clive?
Thank you. That was impressive that you got such consistency in that fiber. What worries me is if you do that on the moon, you're in 1/6 gravity, and getting that droplet to fall. Have you looked at any models of the effects of gravity on that process?
The effect of gravity is very important, but also the size of your system, of your crucible or bushing that you are using. In that case, as a simple answer to your question, I would simply make this bushing, change the height of this bushing, that I could compensate by the hydrostatic pressure, the lower gravity. But this is just a simple approach.
Okay. Thank you.
Do we have any other questions from the audience? And do you have any plan, Alexander, or have you done already some tests in reduced gravity? Is that in the plan?
No, we don't. We first start with vacuum and hopefully one day in reduced gravity, maybe on a parabolic flight.
Very good. So if we don't have any more questions, we move to the final talk from the session. We talked about, thank you, Alexander. So we've talked about landing pads earlier. Now we move to the next stage, which is habitat shielding. And we have Maëlle Mathieu from Polytechnique, Montréal, who will tell us about her research.
Yeah, so I'm going to talk more about what we can do with additive manufacturing more than additive manufacturing. So the idea we were working on for the habitat is, instead of putting the whole habitat, we wanted a habitat more modular and also more easy to print with smaller robots. So we looked at something that has been existing for a few centuries now. It's topological bricks. At the origin, they were used especially to build churches with flat ceilings. So we wanted to go back to see if we could use that to have something very more modular but easy to print. The main challenge we're going to have when we're going to use this type of bricks is that we're going to need to have a really precise geometry and precise manufacturing. But it can be really interesting for this property that it's going to make the whole habitat self-adjusting, and we can also have some missing brick or misplaced brick and still have a stable habitat. So we started by exploring all the topological designs that are existing. So for that, we did go back to the original design from a few centuries ago. So what we learned is we really wanted that type of bricks to be able to print without any support, because we wanted to have something to minimize the resources we're going to use once we are on the moon. So all our type of brick are possible to print without any support. But what we learned when we did this first type of prototype is that we needed for large assembly, as we can see in the smaller image, external constraints, and we weren't interested to have external constraints. So we started to look at if we could add more joint to this type of topological bricks to be able to have a stable habitat without any external joint. So at the moment, we looked at 3 different joints. So we did go back to one of the basics, the Lego joint. It's really the same one as we can see in every Lego bricks. So here the idea is the 2 of them use cavities to block into each other. We also looked at that sliding joint to be able to have something more easily assembled with robots, because the Lego joints ask for really precise positioning with robots. And finally, we looked at something we called rotational joints. So it's something that's kind of mixed the 2 precedent idea with a sliding joint and the Lego joints, that we kind of rotate the brick to fit into each other. These joints, it's really stable, but it's really difficult to obtain in the robotic assembly because it asks for 2 different movements. So we still wanted to know if these properties of misplaced bricks and a stable habitat was still possible when we added a joint. So what we did is we did some simulation to learn how they act when we added joints. So what we learned, if we look at the Lego joint and the rotational joint, we have a lot more stress and a lot more displacement than when we looked at the sliding joint. So the Lego joint and the rotational joint, if they are misplaced, the whole habitat will not be aligned as it should, when the sliding joint still keep its property to be really aligned and self-adjusting. So now we started to work on a more global and larger assembly. So we started to look at really dome and habitat. So our habitat, we are considering that it's going to be buried. So it has this kind of more of eggshell and it's half spheric shape. So what it's going to be composed, we will have 3 different curves that are going to be able to assemble together with panels. Until now, we are really working only with just the Lego joint. We are starting to also look at how the other joint will work in the whole habitat. So we are also been working on another idea for interlocking. So we also wanted outside of the habitat to have something easy to do with tunnels, cable, and things like that. So we developed this kind of pipe. So we have a larger diameter and a smaller diameter, and kind of the corrugation work as the interlocking joint. So they are really able to kind of slide into each other and screw to kind of an infinite level to be able to have this kind of transportation and things like that. So once we had a better idea of what was going to happen with the dome, we really wanted to look at how this kind of panels and joints we work under the different load on the moon, so pressurization, the cover of regolite for radiation, and finally the lunar gravity. So for us right now, what we learned is that the pressurization is going to be our main load On the habitat, we are still working on a full simulation of the full structure of the dome to have a better idea of how they work together to kind of better work in this dome. So what we also learned is that this kind of really precise joint will be really difficult to print in terms of 3D concrete. So we are now looking to use more of sintering to really have something more easy to print and feasible. So that's why, as you can see, until now, all the models are really 3D print with usual material like PLA or ABS, because we weren't able until now to have something working with regolite. So finally, as you can see here, with the simulation working, so that could be one of the assembly possible. So this dome is really working as a dome, but also a tunnel, because we can curve the shape to make a really full cities. Here on the side, we have a model we worked back in December of a 30 centimeter diameter with a robotic assembly for this. So in conclusion, I really talk it really fast. So we really learned that it's still possible to have misplaced brick and working with this type of joint. We are really working on learn more about how it works with thermal and seismic simulation. And we are working on the joint design more in terms of robotic assembly, but also to be able to print it easier when we go with more regular simulant. And finally, we didn't add it in the presentation, but we are working on a full-scale model for next year. We are hoping to test it in one of the northern communities in Canada. So really, we also want this work to be applied on Earth and to spin off in a remote area for this type of construction.
Thank you very much, Maëlle. And we do have a first question from Jerry.
More of a comment.
Yeah.
There's been a lot of work on trying to 3D print and sinter bricks using regolith. And what has been found is 3D printing doesn't work because all these interlocking bricks, the level of accuracy of actually forming what you want to interlock, that is incredibly hard to do. And when you go to shrinking or to sintering, you'll find that your material shrinks.
Yes.
So your shape will, so you have to take that into consideration. So to be honest, most of the work with making bricks that will interlock use extremely simple features. So I would caution you in the future about that.
Thanks.
We have another question. I would challenge Jerry on 3D printing doesn't work, but that can be a side discussion.
Bricks to do this kind of job.
Understood. Second question.
Yeah, it was an interesting talk. My question is about the types of structures you were building. Have you considered pressurization of that structure and how that might influence the joinery option?
So if we go back a little bit here. So yes, we consider pressurization. The only question we are not sure right now if we're going to add more internal layers for infiltration to not have to pressurize the whole habitat or only this internal layer. So it's something we are working on right now, and we hope to have more information by the end of the summer on how we're going to work with that type of pressurization.
Do we have any other question from Maëlle? I do have a question, Maëlle.
Yeah.
So, I mean, Jerry made a very good point about the accuracy needed and the challenges of the processes. There's another challenge, which is the mechanical properties of your individual bricks.
Yeah.
So the more precise your joint, the more demanding it is in terms of toughness and shear, because you will have shocks when your robots try to assemble and so on. Have you thought about what process and what sort of material would be adapted to have the required mechanical properties?
So we are going to start working on the robotic assembly in September, so it's something we know we have to look at, but we really don't need so much research on it until now.
Okay, so I think you could have a good chat with the people making fiber reinforced composite, because there you get some resilience. Clive?
Thank you.
Yeah, it's a bit intrigued about your corrugated tubing.
Yeah.
And it seems to be a screw connect.
Yeah, so...
And that bothers me because of dust on the lunar surface getting in there.
Yeah, so this pipe, we designed it first with the Earth in idea, and then we are starting to make them for the Moon. So what we are thinking to avoid big problem with dust, is instead of having a small one and a big one, and they interlock with each other, we are thinking of keeping it assembled like that, and they add another layer in printing as we go in.
So you won't be screwing them together, is that?
It's possible, maybe not. We are looking at how we can work with the dust to avoid this kind of problem.
Okay.
So it's really new, so yeah.
Thank you.
And we do have one final question over there.
So, Miguel Albino, University of Lisbon. So you have very complex shaped bricks. What would happen in terms of like meteorite hits the structure, breaks a brick? So now you have, how do you repair it? Do you have to disassemble the whole structure because they interlock?
Yeah, so the idea is you have to disassemble it, yes, the whole structure to repair it. We are also looking in the side engine if we could make it so we could only move this brick to break the ore to repair it. So, yeah.
Okay, thank you.
Thank you very much. So that concludes the session. Thank you, Maëlle. Thank you to all the speakers. And now we have a break until 11 o'clock back here for the next session.